Good afternoon, everyone. Thank you for coming. My name is Jinal. I work as a software engineer at Google. And today we will be talking about using gossip protocol for failure detection. Let's get to it in a few slides. So yeah, I was going to give this session in person until the visa decided to turn up late. That's been funny. Nonetheless, it's so good to see you guys. I'm really missing Malmo. Um, so about me, I work in Google Maps. Currently, I'm building ML solution to make maps a safer place. Basically, I work in fraud detection. Prior to this, I have worked at Morgan Stanley and Goldman Sachs as a backend engineer, where in Goldman Sachs, we build end-to-end automation solutions for fairly manual financial processes uh, for the Automation Center of Excellence. So I was the backend engineer before, and then I shifted to ML 2 years back when I joined Google. It's been great so far, learning so many new things. I am passionate about distributed systems, always curious to know the whys of every system, debugging, etc. In my free time, I also carry out outreach activities for women in STEM and children, basically spreading awareness about opportunities in tech and encouraging them to persevere. So yeah, that's about me. So for this session, which is basically building available uh, and reliable systems, and how do we do failure detection in distributed systems? The takeaways for this session is basically, so I love reading about distributed systems. It is actually like a rabbit hole that goes on and on. Once you start reading about it, it's actually like a rabbit hole. So yeah, it correlates with the theme. Yeah. So the takeaways that you can expect from this session are basically how failure detection is very necessary for building highly available systems, maintaining a timely view of the current system of the status. So basically maintaining a timely view of the status uh, of the system is essential to the performance and functionality of distributed systems. So we all use distributed systems everywhere in some shape or form, right? Google Cloud, Amazon, like we all use Amazon, Zookeeper, etc. But internally, we might not know what it is comprising out of, consistency, or what it is compromising out of a consistency or availability. So you'll be able to understand what architecture is best suited to the system that you want to design. I keep reading research papers on distributed systems. So this is also to inspire you to read them if you are interested. And I hope you get interested after this session. I just wanted to check, okay, quick show of hands. How many of you already know about gossip protocols? I see one hand. Oh, that's great. So then maybe this will be like new for uh, people around. So yeah, like it's going to be interesting. Okay, so just a quick recap of CAP theorem. It's very quick recap. Basically, CAP theorem is consistency, availability, and partition. Consistency is basically that all nodes contain the same state. So whenever there is a read request, irrespective of the number of nodes that you use, any server that your request hits should return you the same response. Availability is what we all know, that requests are responded to promptly. Whenever you query something, you should get a response. Partition is basically that part of a system whenever there is a network partition. So basically, your nodes are not able to talk to each other, and the part of a system is completely independent from the rest of the system. Uh, so that is what you mean by partition tolerance, that a system can stay online and functional even when message passing fails. So the CAP theorem basically says that out of the three, C, A, and P, at a time, you will be able to only get two out of them. It's not possible to have a system which has all the three uh, features in it. So we'll have to always, a system designer will always have to make the right compromises to achieve um, any two of them. So yeah, let's start with an example application. So let's say we have an application that has to be available. Let's say you're building sort of an application like Amazon, which always has to respond to your request. Like Amazon rarely says that it's down. So currently we start small and we have 5 application servers as shown. And for fault tolerance, we are also replicating the database into multiple copies. Here you see 5 copies. So let's assume that you have same database, you have multiple copies of it, so that if one of them fails, you also have other copies available. This is replication. So application server, we're going to keep it stateless. It just makes a call to the database whenever you want. And it's agnostic of which copy it's going to. But somewhere, even if the application layer is stateless, we still need to store the state of the system, like how many number of nodes are there, IP address of the nodes. By nodes, I mean the database nodes. So somewhere there needs to be a list. So let's say, let's use first approach where all database nodes themselves are maintaining a list. What happens if one of the node goes down? Now, all nodes have to update their own list saying, okay, S1, let's call it S1. S1 is down, and this has to be communicated to all the S2, S3, S4, and S5. For example, let's say we were using heartbeat messages to check if a database was okay or not, this would lead to n square messages. Basically, if there were 1,000 database servers, it would lead to 1 million messages. So there would be a lot of traffic. So this is difficult to scale. Like there are systems which use this, but it's extremely difficult to scale if you're going to just have like 5 as shown here, like just a small number of servers. This is fine, but it's not scalable. Now, let's say we use a second approach where we use a centralized node to persist node status information. So this centralized node will hold mapping of databases status info. Like it will store, okay, S1, S2, S3, S4, S5 is available, what are his IP addresses, etc., etc. And whenever a node is down, it will update internally. But the problem here, if you can guess, is that it has a single point of failure. If this centralized node goes down, we are left with a broken system. So we're compromising availability here. For 5 application servers, one centralized node is sort of enough to handle the traffic because only 5 are there. So a single node will be able to handle the traffic. But if we were to scale the servers and DBs to, let's say, 10K, then availability will also be compromised. So what we can do to what we can do to mitigate is that we have 2 nodes to store the status information. So instead of the centralized node, like a single one, now we'll have 2. One is going to be primary and other is going to be backup or standby. So whenever one node is down, we'll use the standby. Now, in this case, if any of the server goes down, we are going to make a transaction, like the write that, okay, S1 is down, we'll go to both of them, both the centralized nodes together. I mean, the primary and the backup, it will go as a transaction together. What will happen is this will lead to latency issues. So in case of multiple failures, so many transactions will have to be made to both the nodes, and this will lead to reduced latency. If your system has lesser number of failures, this architecture will work. But if you have higher servers, thus higher failures, this will not really scale well. And again, if the standby replica is down, it needs to be quickly replaced, and we need another failure detection on top of this. So it's crazy. So wouldn't it be better if every node could send a message to a smaller subset of nodes, and then those nodes to other nodes, and eventually all nodes just know everything? So basically, rather than relying on centralized nodes, what if the nodes themselves were sharing information and eventually everyone knows everything? And this is nothing but gossip. Like this is called gossip protocol, which works exactly like gossips or epidemics. By epidemics, I mean infection. Like, if one person in the house is infected with a disease, eventually they spread to two other people, those two to spread to other four people, and eventually, I mean, I'm just giving an example, but eventually the entire house is infected. And this is also similar to gossip. So this is called peer-to-peer gossip protocols, and this is gossip protocol is basically the main motivation is to trade the strong reliability guarantees offered by other costly deterministic algorithms like Paxos or Raft. They are very complex, whereas gossip is like simple. And but in return, we are obtaining very good scalability properties, and we'll see how. Like, we'll go in detail over the gossip protocol here. So uh, this it's believed that gossip protocol was first used in 1987, and like, it's assumed that it was first used in 1987 as described in the paper Epidemic Algorithms for Replicated Database Maintenance by Palo Alto Research Center. So it was first used in Xerox, which was also known as the clearinghouse servers. So the company Xerox used it first for database updation, basically, which is also known as information dissemination. So as I said, that if you maintain a lot of database replicas, whenever a write comes, you have to uh, basically convey the message to all the replicas that you have. And this was where gossip is used first. This paper is considered to be seminal, like the birth of gossip, sort of. So we're going to talk briefly about it. And I really love this paper because it's easy, and it's informative, and it sets the tone right for how gossip started. So as I said, this protocol is inspired by epidemics, human gossip, and social networks. After this paper, there have been hundreds of papers, and all of them are inspired by epidemics. And they're called actually epidemics, epidemic algorithms slash randomized algorithms slash peer-to-peer algorithms, because of the way they work. So just as in real life, the key property of gossiping is the fact that it can spread quickly and be extremely persistent, um, even in situations in which groups change with respect to their memberships and relationships between group members. So it doesn't matter, like, since there is no, I mean, they do maintain a state, but not of the whole. So let's say there are n nodes. Every node does not maintain a list of all n. It basically only has a local information. Like, just like if you were someone, you would just tell something to your friends and not to the entire town. So it's equal to that. Like, a node just has information of other local nodes. It talks to its local nodes, and then they talk to their local nodes, etc., etc. So whenever there are group changes, by that I mean one of the node goes down or another node joins, that node which is joining, I mean, that's how in real it works. That the node that is joining is just given the IP address of one or two other nodes in the entire cluster, and that is enough for all the nodes to know that a new node has joined. So yeah, rumors in society travel at a great speed and reach almost every member of the community. And what's even better is that it does not need a central coordinator. So yeah, this is like fun. So as I said, the motivation for gossip protocol is basically unreliable network. By unreliable network, I mean that anytime uh, it can go down. Unreliable nodes, nodes can go down and new nodes can also come as well. Now, the important point to note here is that out of the cap theorem, I mean, out of the cap, the gossip protocol is basically focused towards AP. It's available. It highly picks up availability over consistency. So it's going to be always be able to respond to a read or write request, and it has eventual consistency instead of strong consistency. And we'll see how that happens. So the paper, which basically talks about uh, how Xerox used gossip protocols for database replication. They were trying to basically build a distributed key value uh, database, which was replicated to 300s of nodes. That was their scale. And all servers basically accepted updates. So it was not a leader follower kind of architecture. All the servers were accepting updates, and lots of concepts that we use today, they are come from them. So all the systems that use gossip protocols, basically it uses the concepts that were stated in this paper. uh, so each update that comes was injected at a single site, and then that propagated to all sites, or later substituted by a later update. So replicas become consistent after no more new updates. So that is what is happening here. So in this paper, three types of epidemics are discussed: uh, direct mail, anti-entropy, and gossip or rumor mongering, whatever that is called. So we'll discuss each one of them. And direct mail is like really simple. So as you can see, direct mail basically means that as soon as the node, um, let's call it the node which is getting a update request, it's immediately mailed. It immediately mails to every other node available in the cluster. So like it's really simple, it's timely, and it seems like reasonably efficient for a smaller number of nodes. So as I've written here, like the formula, capital S is the basically set of all servers that you have. So for each server, just post the mail and update values, and whichever server is basically receiving the update, it changes its value if it needs to change. So per update, you're going to have n messages, assuming that n is the size of the entire cluster. So this is like really, as we see, that's going to be a lot of traffic here. So this is timely and reasonably efficient, but not entirely reliable, since individual sites do not always know about all sites. And the possible points of failure are mail can get lost sometimes. Every node might not have information about all other nodes. So the whole point of this algorithm is that it has to send mails to all the nodes possible. So again, the same issue that if it's not aware of all the nodes, then this fails. So and again, high volume traffic is going to be there at the epicenter because it has to send out like n mails. See, another one was anti-entropy. And this is also really important because even though like the last one, which is called mongering, is used everywhere, a combination of anti-entropy and rumor mongering is used by applications, like practical applications that we see. So anti-entropy turned out to be like really useful. So by anti-entropy, what is anti-entropy? Every site, every node regularly chooses another node at random, and then it exchanges database contents with it. So this is an expensive operation. What they're doing is basically just exchanging their database content, and they resolve differences between the two. So what is going to be happening is every node is going to do that. So if there are n nodes, everyone is going to choose any random partner. They're going to say, okay, what do you have? What do I have? And they're going to exchange, resolve the differences, and that's how eventually all the n nodes become consistent. So anti-entropy is extremely reliable. Like there's no chance of failure because it doesn't need to know about everyone. It's just going to choose a neighbor and exchange information. But it requires examining the contents of the database, and it cannot be used too frequently. Like you cannot keep doing this every now and then because it's an expensive operation because the database is going to be huge. So analysis and simulation show that anti-entropy, while reliable, propagates updates much more slowly than direct mail because, as I said, So it is fault tolerant, and it uses custom protocols to resolve conflicts. And what has been seen and proved is that it takes log n number of rounds to reach consistency overall for n nodes. So we're going to see a simulation of how anti-entropy works. So let's see that. So let's say these are n nodes and the light green node is the one that has the message. So now here you see that in the same round, every node picks up a partner and now they're going to share information. The new information is only there with one node currently. And what we need is every node to become light green eventually. So after this state, I mean, this is what happens after the previous step. So now next round is where again every node chooses another random node and they will start sharing information across. So what happens is now the node here, I think you cannot see, but yeah, the light green nodes, whatever they're communicating with, they will also become light green. Now, again, they choose partners. Also, there is a possibility here that a node which already has the information might choose the node, a redundant node which already has the information. So that's going to be a redundant check, and we'll come as to how to optimize it. So yeah, this is now only two nodes are left to be sent the message to, and yeah, so now everyone knows. So this is how anti-entropy works. It's just like a visual simulation. So as I was saying, what happens here if two light green nodes communicate, which is actually happening here? Uh, it's a redundant, unnecessary operation because they are actually going to exchange the entire database contents. So what was used to optimize it was, instead of exchanging the entire database content, they used to only do improvements like checksum. So it was a sophisticated mechanism where instead of exchanging the entire content, first every database node maintains a checksum of its content, and then first they just exchange their checksums, comparing, and then they compare their full databases only if the checksums disagree. And this scheme saves a great deal of network traffic, assuming that the checksums agree most of the time. Uh, but unfortunately, it is common for a very recent update to be known by some, but not all sites. So this did not occur a lot. Like in this example, as we saw, at least initial few cycles, it will not help even if you had checksum comparison, because only one of the nodes knew the full information. Eventually, when you reach a stage where a lot of nodes are already aware of the information, then the checksum comparison helps. So then a more sophisticated approach was tried to using checksums, which defines a time window, let's call it T. So the time window T is large enough that updates are expected to reach all sites within time T. So each site will maintain a checksum of its database, and additionally, the site also maintains a recent update list, which is basically a list of all entries whose ages are less than T that we have. So basically, T is nothing but it's a large time window where you expect that, okay, every node should have the information. It's just some constant that you set. And then every site will maintain this list, okay, of whatever I have communicated with, whose ages are less than T. And then two nodes, S and S1, let's say, they perform this anti-entropy by first exchanging their recent update lists, and then they use their lists to update their databases and checksums, and then they compare checksums. So only if the checksums disagree, then they compare their entire databases. So this recent update list was also better than the previous one. Like this was just discussed in the paper and it was like interesting because it's an improvement over the previous algorithm. So next is the rumor mongering, where basically this is very similar to the previous one. What happens is all sites are initially ignorant. And when a site, I mean, site is basically a server. Sorry, so I'll use the term server or a node. So when a node receives a new update, it becomes like a hot rumor. And while a site holds a hot rumor, it periodically chooses another site at random. So this happens periodically, and it will choose another site at random and ensures that, and it basically tells the update to the other side, I mean other node. And when a node has tried to share a hot rumor with too many nodes that has already seen it, it stops treating the rumor as hot, and then it retains the update without propagating it further. So what happens is there is one node, it got the update, now it picked up another node at random, it it gave it, I mean, it gave the update to the another node, and it will keep doing this periodically until it's interested to do that. And if it feels like, oh, this node already knows it, um, after a point of time, it stops doing this. So rumor cycles can be more frequent than anti-entropy cycles because they just require one write instead of exchanging the entire database. So they require fewer resources at each site, but there is some chance that an update will not reach all sites. So as I said, it's very equal to, let's say I know a rumor, and it's very hot. I mean, it's a hot rumor, so I'm like very interested to tell everyone. So I'll go around, I'll pick my friend, and I'll tell him, and then he will tell someone whenever he wants to. So periodically this happens, but I keep telling it to, like every day I keep telling it to new people that I know. But once I tell it to someone and he or she tells me, oh, I already know it. If this happens too many times, I'll eventually stop telling people because I'm no longer interested to keep spreading it if the other person already knows about it. So that's what's happening here. Uh, yes. So this is equal to epidemiology literature, where the node that actually has the update, it's called infective. I mean, this is the terms that are used to describe the. I will go to that. Yeah. So site which does not know the update in the entire cluster is called susceptible. The node which has the information and it's actively sharing it everywhere, it's called infective. And a site which has the information but it's no longer interested in sharing it is called remote. Uh, so the proof has been given in the paper, and what we have seen is this requires again log of n rounds to it leads to consistency to all the nodes knowing this with a certain high probability with log of n. So the difference between rumor mongering and anti-entropy is that in anti-entropy, all nodes were exchanging databases by choosing random partner. In rumor mongering, again, a node chooses a random partner. I mean, multiple nodes choose random partners, but they do this periodically until they're interested, and you can tweak those parameters, but it's not necessary that all nodes are not doing this, so it has a probability that not all nodes will have the information. Okay, so the messaging strategies which are used here, and I think even in anti-entropy, are basically push, where I am infected and I'm going to infect people. I mean, I'm an infected node and I'm going to infect other nodes. So nodes with new updates, they send it to other nodes. Pull is where all nodes are actively pulling for updates. So that's another mechanism which was used. And push pull is basically a combination of the two, that if I have updates, then I'll push it. And if not, then I'll also keep pulling for new updates. So a single node does both of them. So uses of gossip. So gossip is basically, in this paper, it was used for database replication. It is also used by Cassandra. Cassandra uses what's called an anti-entropy version of the gossip protocol for repairing data. So super interesting, and you can read more about it, of how exactly it uses. It can also be used for information dissemination, which is actually, I mean, a version of database replication itself. In database, we basically are updating or disseminating the writes. Information dissemination is if there is a new message, whatever, and it needs to be sent to all nodes in a cluster. A very important usage is cluster membership, uh, which is basically a node can have a view of other nodes in the cluster, what nodes are joining, what nodes are leaving, etc. So that's a membership protocol, and gossip is used highly for membership protocols. Failure detection is what was our premise for the talk, which basically means that whenever a node is dead, we want to have that information very surely, because that affects a lot of things. Overlay networks is nothing but uh, you are using gossip to build an overlay network so that you can know to what node you want to send information to. It's like a mapping of this node has this information, this node has this information. It's like a sharding information. So yeah, Plum tree does this. And aggregations is basically to calculate average, sum, max, etc. over a number of nodes. So gossip, where it's used in practical, we already discussed that, but like actual places where it's used, React uses a gossip protocol to share and communicate ring state and bucket properties around the cluster. As I said, Cassandra uses gossip to exchange information about themselves. I mean, the nodes, they exchange information about themselves and about the other nodes that they have gossiped about. This is basically equal, this is equal to maintaining a recent update list so that all nodes quickly learn about all other nodes in the cluster. So it's sort of a membership kind of thing. They're using it. Dynamo uses gossip for membership protocol. Surf, which is HashiCorp, which was also called as console. So Surf by HashiCorp uses a gossip protocol for two purposes. They have an entire layer, for gossip, for failure detection. So to discover new members and failures, and HashiCorp has a really amazing bunch of papers and talks, and even on its own website, they have very mentioned in a lot of detail of how their gossip protocol is built, so that you can read that up. It's super interesting. So yeah, they use Surf uses it for member detection and failure detection and discovering new members. It's reliable, and it also uses it for leader election, like broadcast events, like leader election. Amazon S3 uses a gossip protocol to spread server state to the system. And I think we had found about this because S3 had an outage in 2009, I guess. And yeah, blockchain gossip protocol is used by the miners to communicate the value of nonce to other miners. Yeah. So we saw gossip protocols, and it's important to discuss its strengths and weaknesses as well, because every algorithm comes with its pros and cons. So the strengths of gossip are basically it's scalable. That's the biggest advantage of gossip, because it takes log n rounds to reach all nodes, even in the face of failures and message nodes. Because let's say you have n nodes and one of the nodes fails, it really doesn't care, because it's going to pick something up and it's going to just communicate the information. So log n is it makes it scalable. And each node sends only a fixed number of messages independent of the number of nodes in the network. So that's one more good point. They normally fire and forget. Nodes do not wait for acknowledgement. and it does not take any recovery action if an acknowledgement does not arrive. It's fault tolerant because, as I said, it can operate in networks with irregular and unknown connectivity. And also, one more thing is, if I am a node and if I send a message to some other node, the same information is shared by so many different nodes. So even if one of the routes fail, there are many other routes by which information can flow from its source to destination. So it's fault tolerant. It's robust. No node plays a specific role in the network. So a failed node will not prevent other nodes from continuing to send messages. Each node can leave whenever it wants to. So that makes it really robust. Convergent, because nodes converge exponentially quickly to a globally consistent state. There are parameters that we can tweak so that all nodes receive the information. But yes, it's convergent. And it's decentralized. That was how we started this talk. Like, it's extremely decentralized. It's peer-to-peer. And its latencies are often acceptable if the information is not going to be used immediately because it's eventually consistent. Weakness of gossip is that much of its bandwidth is consumed by redundant information. As we saw, I think, even in Anti-Entropy, two nodes, I mean, even if they know, they might be chosen randomly because it's based on randomness. Gossip protocols, messages are sent periodically. So it does not matter if a node has received 3 new messages. Like, it's not one-on-one. It's going to work with a cycle. So even if I have received 3 new messages, I'll still have to wait for my time to come, and then I'll be able to spread a message. So there is a latency involved. It's not immediate. At least the basic one has certain latency involved. Like, there are other variations of gossip protocol involved. They are randomized, so they are difficult to debug. And gossip protocol, in some situations, cannot scale well. For example, when the rate at which the information is injected in the system exceeds the capacity of gossip protocol. Like, if you're receiving a lot more messages than we are able to send, in this kind of a system, it's very hard to scale well. So what next? We are almost reaching the time, and this is the last slide. So there are a lot of variations, as I said, to the previous one. Mathematically speaking, when does a node stop sharing an update or info? Like, I say that, okay, if I'm not interested, I'll stop sharing it. But when does that happen? So we use a variable K that's used in the paper, actually, that every person hearing the rumor becomes active and it shares the rumor. But when an active individual makes an unnecessary phone call, like, the recipient already knows the rumor, with probability 1 by K, the active individual loses interest in sharing the rumor. So this K is used to formulate so this log of n is based on this K. Like, it's very important to set these parameters right to achieve the final conclusion that that gossip works in log n time. So there are two variations, blind versus feedback. Blind versus feedback is basically where I lose interest. A sender loses interest only if the recipient already knows the rumor. So it uses that feedback. A blind variation is where it loses interest with probability 1 by K, regardless of the recipient. So we are going to use this constant 1 by K, and the person is not, it's after K rounds, he's going to stop spreading the information. And feedback is where they're going to use the feedback, and they are going to stop with every time they contact someone who already knows the rumor, 1 by K probability, their interest will reduce by 1 by K. But the second is counter versus coin, where they use feedback, and they stop sending the information and they maintain a counter on their own side. If they have exchanged the same information like n times with nodes that already have the info, they stop sending the info. So that's it. Gossip versus Paxos, I just thought it's important to touch on it because they solve different things. Paxos, Raft, Zookeeper has Zab. They are highly consistent consensus algorithms. Whereas Gossip, it's not consistent, is eventually consistent. Paxos requires a quorum, which is like more than half of the nodes need to agree on something before it's true. They are CP algorithms in the cap theorem sense. Gossip is AP, as I said. So yeah, I mean, I'll just conclude this by distributed systems need a form of consensus because they're distributed, and every node needs to know what's going on with other nodes. Like it's super important. Effectively choosing the correct consensus, it has to be weighed carefully with the attributes of the system, like what do you need versus uh, what are the necessities of your system that you're building, which is why knowing about these things like help. Gossip is like really simple to implement. It's as simple as spreading a rumor, so it's robust and resilient. It's designed to deal with continuous changes. It's reliable despite peer failures and message loss, and nodes are autonomous. So yes, and there are a lot of other things also. If you keep reading about it, like super interesting. I will attach more references and I'll share the slides. But these were the main papers that I referred to. I am open to questions. I don't know if we have time for that. But you can always reach out to me. I mean, if I was there, it would have been super helpful. But you can reach out to me on Twitter or mail me at Jinal Parikh 410 @gmail. Thank you so much.